Hello friends, I welcome you all to Only Code. I'm your host and host Rahul. Let's get started. In this session, we are going to break down everything you need to know about linked lists, from how they work internally to when and why you should use them. First, we will start with a basic introduction to linked lists. Then, we will explore the internal working of a linked list, how the nodes are connected, and how operations like add or remove actually happen behind the scenes. After that, we will see how to initialize a linked list using its constructor with and without values. We will also walk through some commonly used methods and how they work. Next, we will discuss the advantages and disadvantages of using a linked list compared to other list types like array list. We will go over some of the best practices and use cases so you will know exactly when to use it. And finally, I will share a real world scenario where a linked list can be super useful to help you connect the theory with practical usage. So stay tuned and let's get started. Before we deep dive into linked list, it's important to understand where it fits within the Java collection framework. As you can see in this diagram, linked list is a class which implements the list interface. But that's not all. It also implements the DQ and queue interfaces, making it one of the versatile classes in the collection hierarchy. The list interface itself extends the broader collection interface, which is the root of most collection types in Java. That means linked list inherits behaviors of both a linear list and a queue. What makes linked list special is that it can act both as a queue and a stack, offering methods to add, remove, and peek from both ends. Let's start by understanding what a linked list actually is in Java. The linked list is a part of java.util package, and it's a doubly linked list implementation of the list, DQ, and queue interfaces. That means it can function as a regular list, a queue, or even a stack, making it extremely flexible. Internally, it stores elements in nodes. Each node contains the actual data and two pointers, one to the previous node and one to the next. Some of the key properties of linked list are maintains insertion order. Elements come out in the exact order they were added. Allows duplicate and nulls. So you can store repeated elements and even null values. No random access. Unlike an array, you cannot directly jump to an index. Linked list needs to be traversed node by node. Not thread safe. If you are using it in a multi-threaded environment, you should synchronize it manually. Now, let's take a look at the internal working of a linked list in Java. As mentioned earlier, linked list is implemented as a doubly linked list, and that means each element in the list is actually stored inside a node. Every node contains three things: the actual data, a reference to the previous node, and a reference to the next node. Here is what a typical node looks like in Java. This is the diagrammatical representation of the same. Now, take a look at this diagram. You can see a series of connecting blocks, each holding a value like 15, 8, 74, and 39. First element is called head, and the last element is called tail. These blocks represent nodes, and the arrows between them shows how each node is linked to both its previous and the next node. This two-way linkage is what gives linked list its name, and more importantly, its powerful ability to insert or delete elements from both ends. Let's understand how Java's linked list internally performs insertion at beginning or the end. The first step is to create a new node. We first create a new node that stores the incoming data. At this point, its previous and next pointers are both null. Check if list is empty. If both head and tail are null, this means the list is empty. In this case, we simply assign head equals to node and tail equals to node. Now, the newly created node is both the start and end of the list. If the list already has elements and we want to insert at the beginning, set node.next equals to head and head.previous equals to node and update head equals to node. This pushes the new node before the current head. If we are inserting at the end, set node.previous equals to tail, tail.next equals to node, and update tail equals to node. This adds the node after the current tail. Update the size. Regardless of where the node is inserted, the final step is to increment the size of the list by 1. Let's take a simple example of a linked list containing 3 elements 7, 12, and 46. Now, suppose we want to insert a new element 81 at the beginning of this list. When we perform this insertion, 81 becomes the new head of the list. The final structure of linked list will now be 81, 7, 12, and 46. Let's break this operation step by step. Initially, the linked list contains 3 elements 7, 12, and 46. To insert 81 at the beginning, we first create a new node with the value 81. Since the list is not empty and the insertion is at the start, we update the new node's next reference to the current head. Set the existing head's previous reference to point to the new node. Then, we update the head to this new node. The size of the linked list is increased by 1 and the entire process completes in constant time, that is, big O of 1. Moving on to the process of inserting a new element at a given index in a linked list. First, the index is checked to ensure it is within the valid range, that is, from 0 up to the current size of the list. If the index is out of bounds, the linked list throws an index out of bounds exception, preventing any invalid operations. Once the index is validated, we create a new node that contains the data we want to insert. Next, we traverse the list to reach the target position. To optimize the performance, the traversal direction begins either from the head or the tail. This is decided based on whether the index is in the first half or the second half of the list. Once at the correct location, we update the pointers. The new node's previous is set to the current node's previous and its next is set to the current node at the index. Similarly, the adjacent nodes are updated to point to this new node, maintaining the integrity of the links in the list. There are two important edge cases to handle. If the index is 0, the new node is inserted at the beginning and becomes the new head. If the index is equal to size of the list, the node is inserted at the end, becoming the new tail. Finally, after a successful insertion, the size of linked list is incremented by 1. We'll see an example to understand the insertion process better. Consider a linked list with 3 elements 7, 12, and 46. We want to insert the value 81 at index 1. Since index 1 is within the valid range of 0 to 3, we proceed by creating a new node with the value 81. We then traverse the list to reach index 1, referring to that node as current. Next, we update the references. Set node.next to current, node.previous to current.previous, current.previous.next to node, and current.previous to node, rearranging the nodes for better visual perception. Finally, we increment the list size by 1. The time complexity of this operation is big O of n, where n is the number of nodes traversed to reach the target index. Let's now understand how deletion works in a linked list when removing elements from either beginning or the end. Before performing any deletion, we first check if the list is empty, that is, if the head is null. If it is, deletion is not possible, and a no such element exception is usually thrown to indicate this. To delete the first element, we simply move the head pointer to head.next. If the head is not null, we disconnect the old node by setting head.previous to null. But if the new head is null, that means the list had only one element, so we set the tail to null. To delete the last element, we move the tail pointer to tail.previous. If the new tail is not null, we set tail.next to null to disconnect the last node. And again, if the new tail is null, the list had only one element, so we also set the head to null. After a successful deletion, we decrement the size of list by 1 to reflect the change. Let's take an example of a linked list containing 4 elements 81, 7, 12, and 46. Now, if we perform a deletion from the end, the last element, that is 46, will be removed. After this operation, the linked list will have just 3 elements 81, 7, and 12. The tail pointer is now updated to point to the new last node, which is 12, and its next reference is set to null. Let's break down this example to understand further. To delete the last node, we first check if the list is empty. Since it is not, we proceed by moving the tail pointer to tail.previous, which points to the node with value 12. As the new tail is not null, we update tail.next to null, effectively removing the reference to the node with value 46. Finally, we decrease the size of list by 1 to reflect the deletion. The time complexity of this operation is big O of 1. Moving on to how a linked list handles deletion from a specific index. Before anything else, the index is validated to make sure it falls within the range from 0 to size minus 1. If the index is out of bounds, an index out of bounds exception is thrown. Once the index is validated, we navigate to the node at that position. To improve efficiency, the traversal starts either from the head or the tail, depending on which is closer to the target index. Now comes the actual deletion. We adjust the pointers. The previous node's next is set to point to the current node's next. Similarly, the next node's previous is updated to point to the current node's previous. This effectively removes the node from the list without breaking the chain. Handling edge cases. If the index is 0, it means we are deleting the head node. So we just move the head to head.next. If the index is size minus 1, we are deleting the last node. So the tail is updated to tail.previous. Finally, we reduce the size of linked list by 1 to reflect the deletion. Let's understand this process with an example. Consider a linked list containing 4 elements 81, 7, 12, and 46. We need to delete the element at index 2. Since the index is valid, we traverse the list to reach the node at index 2, which we'll refer to as current. To remove it, we update the surrounding references. Current.previous.next is set to current.next, and current.next.previous is set to current.previous. This effectively bypasses the current node, removing it from the list. Finally, we decrement the size of list by 1 to reflect the deletion. The time complexity of this operation is big O of n, where n is the number of nodes traversed to reach the target index. Let's take a look at how searching works in a linked list. To begin the search, we start traversing the list from the head node, the very first element in the list. As we move through the list, we compare the value of each node with the target value we are looking for. This comparison continues node by node, all the way through, until we either find a match or reach the end of the list. If a match is found, we return the index of the node, or the node itself, depending on the implementation. If we traverse the entire list without finding the target, we return -1 or null to indicate that the element is not present. Consider a linked list with 4 elements 81, 7, 12, and 46. Now, let's search for the value 18 in the list. We begin the search from the head of the list, where the first element 81 is not equals to 18. So, we move to the next node. We continue this process, checking the elements 7, 12, and 46, but none of them match 18. Eventually, we reach the end of the list, without finding the target value. As a result, we return -1 to indicate that 18 is not present in the list. The time complexity of this search operation is big O of n, where n represents the number of elements in the linked list. Talking about how a linked list is initialized using its constructors. Default constructor. When we use the default constructor, an empty linked list is created. At this point, head is set to null, tail is also null, and the size is initialized to 0. This means the list is ready to store elements but currently contains none. Constructor with collection. There is also a constructor that allows you to create a linked list directly from an existing collection, such as an array list or any other collection type. This constructor copies all the elements from the given collection into the linked list, preserving their original order. It's a convenient way to convert other data structures into a linked list in just one line of code. So, whether you are starting fresh or building from an existing dataset, linked lists provide flexible ways to get started. Let's now go over some of the most commonly used linked list methods, grouped by their functionality. Insertion methods. These methods allow us to add element to the list. Add adds the element to the end of the list. Add index, element inserts the element at the specified index. Add first inserts the element at the beginning of the list. Add last adds the element to the end, same as add. Deletion methods. These methods are used to remove elements. Remove removes the first element from the list. Remove index removes the element at the specified index. Remove first removes the head of the list. Remove last deletes the last element. Access methods. Use these to retrieve elements without removing them. Get index returns the element at a given index. Get first returns the first element. Get last returns the last element. Peek retrieves the head of the list without removing it. Useful in queue-like operations. Utility methods. These help with checking or modifying the list state. Contains. Check if the element exists in the list. Index of. Returns the index of first occurrence. Size. Returns the number of elements. Is empty. Returns true if the list has no elements. Clear. Removes all the elements from the list. These methods make linked list a versatile and easy to use data structure for a variety of use cases, from stacks and queues to general purpose lists. Now I'll be showing you all these methods in code one by one. Let's create a linked list of type integer named nums as new linked list. We will start from the insertion methods. The first method we are going to cover is add. Let's add few numbers to this list. Printing the list. These numbers are successfully added to the list. Next insertion method we'll cover here is adding an element at a particular index. We will add an integer 18 at index 3. Let's print the list after that. We can see in the output that 18 is added to index 3. Next, we'll be covering the add first and add last methods. As by the name, we can see add first adds an element in the starting and add last add an element at the end. Let's print the list. In the output, we can see 3 is added at the starting and 12 is added at the end. Moving on to deletion methods. We will start from the first method, which is remove element. It removes the given element from the list. More specifically, it removes the first occurrence of the given element from the list. Let's try to delete element 3 from the list. In this example, we have typecasted 3 to integer object. This is done so that the compiler does not confuse between the method remove by index and remove element. Let's print the list after that. Now we can see the first occurrence of 3 is removed from the list. but still the second tree exists there. Next deletion method is remove an element from the given index. In this case, we will supply the index, printing the list after that. Element at index 2 was 3, which is now removed. Similar to add first and add last, we have remove first and remove last methods. By the name, we can see that remove first removes the first element and remove last removes the last element. Let's print the list. In the final output, we can see the first element 1 is deleted and the last element 12 is also deleted. Now let's move on to the access methods. We will start from the getIndex method. This returns the element present at the given index. Let's try to get the element at index 2. The element at index 2 is 4, which is printed. We also have the getFirst and getLast method in LinkedList. Let's print both of these. The first element printed is 2 and the last element is 5. There is one more access method known as peek. It returns the head of the list without removing it. It works similar to getFirst. 2 is printed to the screen, which is the head of the linked list. Now let's talk about some utility methods of linked list, starting from the contains method. This method checks whether the given element is present in the linked list or not. Since 4 was present in the linked list, it returned true, and 72 was not present, so it returned false. Another utility method is indexOf. It returns the first index of the element given. The index of first occurrence of 2 is 0, since it is the first element, and 34 does not exist in the list. Therefore, this method returned -1. Another utility method is isEmpty. It returns true if the list is empty, otherwise it returns false. Since the list is having elements, this should return false, as expected. The last utility method we'll cover here is clear. It clears the list, that is, removes all the elements from the list and makes the list empty, printing the list after that. We can see the list has become empty now. There are many advantages of using linked list. Let's discuss a few. Efficient insertions and deletions. One of the biggest strengths of a linked list is its ability to insert or delete elements at the beginning or end in constant time. Unlike arrays, there is no need to shift elements around, making these operations super efficient. Supports large and dynamic datasets. A linked list is dynamic in nature. It grows and shrinks as needed. So, if you are working with a dataset where the number of elements is not fixed or keeps changing, linked list handle that gracefully without worrying about resizing like you would with an array. Flexible memory allocation. Memory is allocated dynamically for each new element. This means linked list uses only the memory it needs, as opposed to arrays, which allocates memory for all elements upfront, sometimes leading to wasted spaces. Efficient for queue and stack operations. Linked list is an excellent choice for implementing queues, FIFO, and stacks, LIFO. Adding or removing elements from both ends is fast and efficient, which is exactly what you want in these data structures. While linked lists offer some great advantages, they also come with a few notable disadvantages that you should keep in mind. Slower iteration. Linked lists are not optimized for random access. If you want to access element at a specific index, the list has to be traversed from head or tail, which makes iteration slower compared to arrays that support direct indexing. Extra memory usage. Each node in a linked list stores not only the data but also pointers to the next and previous nodes. This means more memory is used per element compared to arrays, which only store the values themselves. more complex structure. The internal structure of a linked list is more complex. Managing multiple references for each node adds to the overall complexity, both in terms of logic and potential for bugs. Not cache friendly. Linked lists don't take advantage of CPU caching as arrays do. Since elements are scattered throughout the memory and not stored contiguously, iterating through them can be slower due to frequent cache misses. So while linked lists are great for dynamic data and frequent insertions or deletions, they might not be the best choice for scenarios that require fast lookups or high memory efficiency. Let's wrap up with some important best practices to follow when working with linked lists. Use linked lists for frequent insertions and deletions. Linked lists are best suited for use cases where you frequently add or remove elements, especially at the beginning or end of the list. These operations are highly efficient with constant time complexity. Avoid random access. Linked lists are not meant for frequent access by index. Since elements are not stored contiguously, accessing an element at a specific position takes big O of n time. For fast random access, an array list is a much better choice. Minimize memory overhead. Remember that each linked list node stores extra references to the next and previous nodes. This can lead to significant memory usage, especially in large lists. So use linked lists only when the benefits of dynamic insertion and deletion outweigh the memory cost. Optimize for queue and stack implementation. If you are building a queue FIFO or a stack LIFO, linked list is a perfect fit. It provides efficient add and remove operations at both ends, making it ideal for these data structures. So, to summarize, use linked list where it shines in dynamic insertion heavy use cases and avoid it where fast lookups or minimal memory use are more critical. Now that we understand how linked list works, let's look at some real world use cases where it proves to be ideal data structure. Dynamic memory allocation. Unlike arrays, a linked list can grow and shrink dynamically. This makes it a great fit for applications where the size of collection keeps changing, like caching systems, session tracking, or job queues, where memory needs to adapt on the fly. Real-time data processing. Linked list is highly efficient when it comes to adding or removing data at both ends. That's why it's commonly used in real-time systems like data buffers, messaging queues, and streaming platforms, where quick and continuous data flow is essential. Undo redo functionality. Behind the scenes, a linked list can be used to maintain a history of changes. You can move backward or forward through the list to undo or redo operations quickly and efficiently. So whether it's dynamic memory needs, real-time data pipelines, or managing user actions, linked list is a powerful choice in the right context. Let's explore a real-world scenario where a linked list fits perfectly. Task scheduling. Let's move on to the code editor. We will be creating a task scheduling example using the linked list. Before going into the code, let's understand the structure we are going to follow. We will define a class named task, which is having a name, and a method called execute, which is responsible for running the task. These tasks will be managed by the task scheduler, which will be responsible for scheduling new tasks, executing the currently present tasks, and displaying all the tasks present in the current task queue. After that, we'll be having a main driver class named task scheduling example, which will handle all the responsibilities for creating the task, feeding these tasks to the task scheduler, and executing them one by one. Let's begin. We will begin by defining the task class. This class will be having a property named name. Also, we will create a corresponding constructor. This class will be having a method named execute, which will be executing the task. In this method, we will simply print a line executing the task name. For now, we are not implementing any functionality within the execute method. Let's create a getter for the name field. Task class is completed. Now let's move on to task scheduling class. This class will be containing all the tasks. It will be responsible for executing these tasks in a FIFO order and also displaying all the tasks currently present in the task queue. Let's define a linked list of type task named task queue. In the constructor, we will be initializing this task queue as empty list. Let's define a few methods for this class. The first method will be scheduling a new task. In this method, we'll be simply adding this task to the task queue and then print a message that the task is scheduled successfully. Now let's define a method for processing all the tasks present in the task queue. The task will be processed in FIFO order. We will continue processing the task until the queue becomes empty. And until the task queue contains some tasks, we will be polling elements one by one and executing them. The poll method retries the first element and removes it from the list. And finally, we will define a method to display all the tasks present in the task queue. We will start by checking if the queue is empty or not. If task queue is empty, we will simply print the queue is empty and return from the function. If it is not empty, we will be printing all the tasks one by one. That's it for the task scheduler class. Let's move on to the driver class. I have copied some tasks which I will be printing here. After that, we will be creating a task scheduler and scheduling these tasks. Let's now display all the tasks present in the queue. Let's run the program. There was a slight mistake in the schedule task method. We have printed the message as task. Task is scheduled successfully. Instead of that, we should be printing task.getName is scheduled successfully. Let's move back to the driver class. Let's run the program. We can see when we schedule the task, we receive the message task 1 is scheduled successfully and so on. And when we display all the tasks present in the task queue, we can see there are 3 tasks currently present, task 1, task 2 and task 3. Now let's process these tasks. Running the program again. We can see that our task scheduler has processed all the tasks one by one. We have successfully implemented the functionality of a task scheduler using LinkedList. Thanks for watching. That's it for this video. Don't forget to like, share and subscribe. We'll see you in the next one.